stretch will increase. Now we're going to use all this and use the method of calculus to obtain the work done in various cases. Now look at this graph of force against displacement. You can see the force does not remain a constant throughout the displacement. So how do we measure the work done? What we do is we take a very small strip of displacement dx. So consider a very small displacement dx where the force remains a constant. We will assume that during this displacement dx, the force will remain a constant. And so, what is the small work done during that small displacement? dw equal to force multiplied by that dx. Now, if the displacement now takes place from x equal to x1 to x equal to x2, what all we need to do is integrate this dw from x equal to x1 to x equal to x2 to get the total work done. So we say w equal to integral x1 to x2 of f dx. And we will be able to calculate the total work done that way. Alright. First of all, we will consider work done in stretching or compressing a spring. I just showed you that in order to stretch or compress a spring, the force will depend on the amount of stretch. Alright. Now, here I have a spring. The figure shows a spring fixed to a support. If I apply a force, a compressing, now what I showed you here is a stretching force. Is that right? In the same way, you can also compress a spring. Now, here a force F is applied to compress the spring. Now, you can see the force has actually compressed the spring a distance dx. So from this initial length of the spring, it has been now compressed by a small displacement dx. Now, in order to compress the spring further, if you want to compress the spring further, your force needs to be bigger. As you compress the spring more and more, you need to apply more and more force. So, a greater displacement x requires a greater force. That means the force keep on increasing with the displacement, and we say the force F is proportional to the displacement. I just showed it to you earlier, and I can write it as F equal to kx. Now this k, what is this k? This k equal to F over x. It is the force needed to produce a unit displacement. And that is called the spring constant. That's right. K is called the spring constant. What is the unit for measuring that spring constant? Force is measured in Newton. Displacement is measured in meter. Therefore, K, the spring constant, is measured in Newton per meter. How many newtons of force is required to stretch that spring by 1 meter? That is the value of K. In fact, many springs have different K value. Is that right? Small K value to a very high K value. The spring for the suspension of a car has a great K value, whereas the spring that you use for your pen has a small K value. Alright, now if the spring is compressed from an initial position x equal to x1 to a final position x equal to x2, then the total work done, so the spring is compressed from here to here. And remember, in order to compress the spring to a very small displacement dx, the work done will be F dx. And therefore the total work done when the spring is compressed from an initial position x1 to a final position x2 is W equal to integral x1 to x2 of f dx, and in the case of the spring, this f equal to kx, and this k is a constant, we can bring it out of the integral sign. So that will be k times integral x1 to x2 of x dx. What is integral of x dx? It will be x squared over 2. That will be k times x squared over 2, x changing from x1 to x2. Now if you apply the upper limit minus the lower limit, you get the total work done is k over 2, bring that 2 outside, k over 2 x2 squared minus x1 squared. This is a measure of the work done when a spring is stretched from an initial length, initial position x1 to a final position x2. Alright, let's do a problem. A particular spring has a force constant of 2.5 times 10 to the power of 3 Newton per meter. This is the K value. How much work is done in stretching the relaxed spring 6 centimeter? Well, you need to stretch it to 6 centimeter. That means you can call the initial position 0 and the final position 6 centimeter, can't you? Yes. Now, how much work is done in stretching the spring an additional 2 centimeter? Well, the force involved in stretching the spring is identical to the force required to compress it. So, the law F equal to Kx is valid for stretching the spring or compressing the spring. And therefore, the equation we developed as W, the work done, equal to K over 2 times x2 squared minus x1 squared is equally applicable for stretching the spring or compressing the spring. That's right. So you got K equal to 2,500 Newton per meter. The spring is stretched from a position x1 equal to 0 to x2 equal to 6 centimeter, which is 0.06 meter. So this is x1 equal to 0. We measure it from here. And this is x2 equal to 0.06. That means this amount of stretch is 6 centimeter, which is 0.06 meter. So what is the total work done? Work done is integral x1 to x2 of f dx, and we can replace f by kx, where k equal to 2,500 Newton per meter. So I replaced f by kx, where k is 2,500, and x1 is 0, x2 is 0.06. And 2,500 is a constant that comes out, and integral 0 to 0.06 x dx, and integrate x dx, we will get x squared over 2. That will be 2,500 x squared over 2 from 0 to 0.06. Well, apply the upper limit. We can ignore the lower limit because the lower limit is 0. And that will be 2,500 times 0.06 squared over 2, and that is 4.5 joules. In order to stretch the spring from its relaxed length to through a distance of 0.06 meter is 4.5 joules. Well, our B part, how much work is done in stretching the spring an additional 2 centimeter. So now you have stretched the spring 0.06 meter. You need to stretch it by an additional 2 centimeter. Means if your x2 is 0.06 meter, your x3 is 0.08 meter. So the spring is stretched from its position x2 equal to 0.06 meter to to x3 equal to 0.08 meter. Therefore, we can still use the same equation, but your x2 is 0.06, x3 is 0.08, your k value is the same, is that right? So that will be w equal to 2500 integral 0.06 to 0.08 x dx. That will be 2500 x squared over 2. Lower limit is 0.06, the upper limit is 0.08. Alright, we apply the upper limit, replace x by 0.08, minus, replace x by 0.06, and that will be inside this bracket. So that is 2500 over 2, we take that to outside, multiplied by 0.08 squared minus 0.06 squared. Remember this 2 has come out. And what's that equal to? That is 3.5 joules. So, in order to stretch the spring end initially by an amount of 6 centimeter, we used how much work? 4.5 joules. To stretch it an additional 2 centimeter, we've done 3.5 joules. If you want to stretch another 2 centimeter, tell me, will the work done be this, greater than this, or less than this? Will be greater than this, because as you keep stretching, you need to apply a greater force. Alright, another one. A 200 Newton force stretches a spring by 10 centimeter. What is the work done in stretching the spring by 15 centimeter? Well, in this case, we are not given the value of K, the spring constant. Is there sufficient information in the problem that lets you do that? Yes, look at this. A 200 Newton force stretches the spring by 10 centimeter. F equal to Kx. Is that right? Now our F is 200 Newton, X is 10 centimeter, 0.1 meter. And you know that the stretching force on a spring is F equal to Kx. When F equal to 200 Newton, X equal to 0.1 meter, therefore we can find that K. K equal to F over X, that is 200 Newton over 0.1 meter, that is 2000 Newton per meter. I hope you understand the way I write this. Newton per meter, Newton divided by meter is the same as Newton meter to the negative 1. This is the standard way to write the unit, and not Newton per meter with a slash. It must be Newton meter to the negative 1. Alright, now that you know the value of K, we need to find the spring is stretched from a position x1 equal to 0 to x2 equal to 0.15 meter. So, this is x1 equal to 0, and the force F stretches the spring to x2 equal to 0.15 meter. The work done is integral x1 to x2 of f dx. And what is F equal to? F equal to Kx, where K is 2000. That's right, where K equal to 2000 Newton per meter. So, the work done will be integral 0 to 0.15, x1 to x2, 2000 x dx. That will be 2000 comes out, 2000 times integral 0 to 0.15 x dx, and x dx integrated gives you x squared over 2. Lower limit is 0, the upper limit is 0.15. Here again, the lower limit does not give you a value, so you don't need to worry about it. So, simply replace x by the upper limit. That gives you 2000 times 0.15 squared over 2. That is 22.5 joules is the amount of work that is done in this case. We developed here.